work I have done when I was at Columbia University actually is already a little bit of updated. I mean, this is 1 year before. So given the fast development in the machine learning area, 1 year is long time. But anyway, I think here I can find some interest in embedding models. Hopefully, you guys like this type of work. So today, in my work here, the main problem. So, or in the general embedding method, the objective is to learn representations of different objects by their relations, right? So in this work here, we're thinking, okay, we want to characterize only the relations that are meaningful. We learn this type of, we learn embedding representations to capture only this part of relations, not noisy relations. So this is the main theme of today's work. And all the work is based on the basic model, exponential family embedding model. I think Maya Rudolph was here last semester, right? She visited once. She talked a little bit about exponential family embedding a little bit. So we're using the same model. Actually, we were working in the same office when I was in David Blatt's lab. Okay. So what is an embedding model? Basically, it learns vector representations of objects, say words here, from their relations. The method is to predict the presence of a word given its context. Here, we want to predict the representation of illustrate, and the context will be to and word to vec. You can make a larger context window, but these are all like detailed techniques. And this type of method can be applied to other items. So the philosophy is similar, right? You have a shopping basket, they appear together, they have some relation. And you use other items to predict you take out one, use others to make prediction of this one, say cream cheese, how many bags of cream cheese in this shopping bag given other items, okay? And you take out bagel, use the other items to make the prediction, okay? So with this type of setup, we use exponential family distribution to model the conditional distribution here. This is our conditional distribution. So the distribution of one item is count given all other items in the same shopping basket. Okay. And there are three elements in this embedding model. It seems like complex, but really these are three key elements here. One is how to define the context. Okay, so this depends on the application, right? You need to consider the relation between the thing you're going to predict and the context. So when you define this context, you're actually using some relation, and that kind of relation will be embedded in the vector representation. The second one is the conditional distribution. Remember, the exponential distribution is defined by the sufficient statistics, and there, once you have that sufficient statistics here, and then you have the distribution, right? And also embedding structure, that means how these vectors are shared among items, right? For example, with word, each word use one vector. Each item use one vector. Sometimes you want the atom to use the same vector when it appears at the target to be predicted. And when it is appear in the context, so same vector, or you can use different two separate vectors for the representation. So this is the embedding structure. The parameters to learn are actually these embedding vectors, alpha and rho. So each j here will be one item, one word, like that. Okay. So this method can be applied to quite a few types of data. For example, movie ratings, right? So movies viewed by the same person, you take out one movie, use other movies, ratings of other movies to predict the rating of this movie taken out. And then you can capture the relation among movies. And bird embedding. So there, we're using eBird dataset. There, birders go off do some bird watching activities, and then for the same for bird species reported by the same person, probably there are some relations, right? I take out one bird species report by the person, use other species to make the prediction, make the conditional probability and fit the model. And also word embedding. Okay, so this is the basic embedding model. And now let's think about, are all these relations related to the application, or are all these relations interesting? So let's see one example here. Suppose I go to Walmart and I buy something, and I say I buy bagel, cheese, and egg, right? But you know, in Walmart there are many more things, right? For example, I don't buy bread because I have bagel already, right? I don't buy kayak. I have never bought a kayak. Okay, so when we form this conditional probability, the question is, do we want to make predictions of these zero entries, right? Sometimes these zero entries are meaningful. For example, bread here, it is like same thing as bagel, right? They're mutually exclusive. But for kayak, it's not related with bagel. So for some zero entries, we want it to be in the model. For some other zero entries, we don't, right? How to differentiate these two entries? We use a zero inflated model, and it has an exposure explanation. So what is the exposure concept is from this paper. So they're using this exposure concept to do recommendation. Here, when I say an atom is exposed, I mean it is related to these atoms bought in the same basket, right? Bread is related to bagel, so there is some relation. We want to capture this type of relation, okay? Kayak, I will say, okay, it is not exposed to this type of relation, two items in my basket. I don't want this type of relation. But how do I decide whether one item is exposed or not? I flip a coin. I use a generative model, basically. I flip a coin and decide whether one item is exposed or not. Or if I have some features, I have some covariance V here. Suppose I'm buying food. In this shopping trip, I'm going to buying some food. So then kayak is not in my consideration at all, right? So in this sense, I can also this type of feature can also help me to decide whether one item is bread is exposed or not. Kayak is probably not exposed. Okay. And here is the model. Exposed means whether this item is involved in my in items I have bought in my basket. So basically whether there is a relation or not. Okay, so given the context, I have 3 bagels, 3 eggs, and I have an atom. I want to decide whether this item is exposed to this kind of to this context, I would say, or in this shopping trip. If it is exposed, and then the relation is meaningful, and I want to capture this relation with my embedding model. Okay. If it is not exposed, it is 0 because it is 0 by itself. Okay. So this is like a zero inflation model, and here is the formal definition of the distribution. 2 cases, either so the Bernoulli vector Bj is the indicator of exposure, right? So if it is exposed, this is the basic exponential family embedding model, or it is 0. Okay. If we check the model a little bit more, and I mean this model can be so B here is a hidden variable. It can be optimized by either just use pure marginalization. There is nothing fancy here, right? You have 2 choices. The marginalization of B only involves 2 terms, not hard at all. Okay. You can also use EM if you choose to, but EM lower bound helps you to identify what's going on here. So if you use the EM lower bound, you can see that. I mean, in EM, you calculate the posterior probability, right? And the posterior is given the atom to be predicted, and also the context, whether this atom is exposed or not. If the count is larger than 0, we say it is not exposed at all. We are sure about that. When it is 0, there is a choice, right? The posterior probability is mu, and you put mu in this EM lower bound. You can see that mu will go here. This is the basic embedding model, plus an extra term. When you optimize the embedding model, meaning that you are optimizing you're learning your embedding vectors, these atoms with 0 count will have lower weight here, right? Remember that mu is always smaller, less than or smaller or equals to 0. Okay. So this is another angle to look at this model, downweighting zeros. Okay. Learning the model is straightforward. You just maximize the likelihood of the model. Again, as I just mentioned, you can directly marginalize out the hidden variable, and then you have likelihood for 1 conditional probability, and then you add up for all the likelihood from all conditional probabilities, and then maximize the conditional likelihood, and then you get the model. So in the real optimization, we use stochastic gradient. We just randomly choose a subset of all these target contact pairs. Okay, I don't know why we always automatically flip pages. So for these 0 entries, we take subsamples. So this is just a straightforward stochastic gradient. Sometimes when there might be more items involved in word embedding. So if you remember, there are like 2 types of conditional probability. One is Bernoulli conditional probability. The Bernoulli conditional probability is not so correct. It's basically asking, okay, I take this word away, and there is a space. I'm going to fill one word there. The question is to ask, okay, whether I take one word, the first word, is this word there? Yes or no? Second word, is this word there? Yes or no? So possibly you can get multiple yes answers for that single space, but actually there is only one word, right? In this sense, the model is wrong. But for computational reason, it is fast because the model is decomposable. And the other one is categorical distribution. Basically, you're asking the question, which word is that position? So the position and the word is missing. Okay. This model is correct. So here is, I'm considering the question, if we are going to use the right distribution, the categorical distribution, so how do we apply this exposure model to this type of distribution here? The model assumption is like this. So I will have an exposure vector. Basically, I will black out some possible choices from this categorical distribution. And then the resultant categorical distribution only have fewer choices. Okay. So this is for the word embedding model with categorical distribution. The optimization is more complex. Again, you will have the problem like decomposing the objective. Remember, in the basic word embedding problem, the people use different techniques. For example, noise contractive estimation. That is to solve the normalization problem, right? We will have the same problem here, but somehow we managed to find a lower bound to solve the problem. Okay, so this is a hidden variable. So again, you need to marginalize out this hidden variable. See that? You're saying frequent word and less frequent word. Okay, yeah. So again, it's similar to the Bernoulli model for these infrequent words. And in learning, the model actually can take care of these infrequent words automatically by like downweighting these zeros. Yeah. So I think I can go back a little bit and let's see. Here. Yeah. So again, there is a difference between the prior and the posterior. So in the prior, we don't really care about the frequent words, infrequent words, frequent items, infrequent items. But in the posterior, for zero entries, if there are a lot of zeros, and then these items will have larger probability to be, not exposed. So for infrequent items, you will get smaller probability here in the posterior. So the model will naturally consider this part. Actually, this is one benefit of using such a model. So this entry here. Okay, so and then experiment. we have conduct experiments on several data sets, and we compare like log likelihood, but it's not really log likelihood, it's just a pseudo likelihood. We can improve the pseudo likelihood, and also we do some tests of robustness of embeddings. So this is the experiment. We use the original embedding model, and we use our model. But for each model, we do two experiments. One is with the original data, and the other one is to specify this data a little bit. So basically, for the bird species, we just truncate some positive observations to increase the number of zeros. And then we discover with our model, the embedding vectors does not change a lot. So basically, our model will give you similar embedding vectors and embedding distributions. But with the original model, there is a big change. So we are thinking this problem in this way, because in real bird observation, right, it's often the time there are birds, but you cannot see them. In the data we get, maybe it's already specified by the nature. The question we are asking is if we further specify the data, the embedding does not change. That means if we could get the real data, probably our embedding vector will be similar. But with the original embedding model, maybe, embedding vectors will be very different. Okay. And also with MUI data, so we check what type of items will have higher exposure probability. So here this is one plot to answer your question. With higher rating frequency, so basically these movies will get higher exposure probability, right? More frequent items get higher exposure probability. At the same time, you can see that here, there are some dots here, not rated very frequently, but higher exposure probability. So because these movies get low ratings, here in the experiment, we somehow mix the movies not watched by a user and the movies with low ratings. We think they have similar meaning, right? The user do not like these movies. And finally, these movies with lower ratings get higher exposure probability because, okay, probably in the conditional probability, the model is more likely to expose this movie in the context. And finally, the context can still comfortably give a low rating to this movie, for example, 0. So this is one explanation for the movie data. And for bird embedding, after the model fit, we see that for this owl, it's basically more active during night. So this is from the calculation of the exposure probability from covariates. For word embedding, we use part of speech, these tags as the covariates to fit the exposure probability. In that sense, the part of speech tags will explain why a word is missing there, right? So for example, if you say battle, the battles won't be there, right? In that sense, part of speech of tags will explain some probability that why some words will be missing at these locations. And then the embedding model can focus more on the real meaning of these words. So you can see that these plurals are ranked at the top when comparing similarities to the original word. This is for the zero inflated embedding part. Any questions? If no questions, we will move. Yeah, similarity. Yes, yeah. Yeah. So these battles appear at different places only because of the grammar constraints, right? So that part of like difference will be explained by part of speech tag. Okay, so let's see the second part. Second part is about context selection. Now we begin to consider context atoms. It's like mirror of the first part. The thing is, if I do buy kayak right here in my shopping basket, the question is when I make the prediction of bagel, should kayak be in the context, right? Maybe not. So the question is, the problem is we want to use some selection mechanism to remove some unrelated items. So we introduce a set of hidden variables here to take out unrelated items. Again, this is a generative model. B is sampled from the prior distribution, and then we finally marginalize out B vectors. So this is the setup of the model. It's somewhat like the attention model, but in a probabilistic approach. So how to decide values of the selector B? We generally set our prior and then do marginalization, use variational inference. This is the Bernoulli prior. And we have the joint probability here. The prior, and this part is the embedding model, exponential family embedding model. And we need to do inference. And we use variational inference. So give me a sense, how many of you know variational inference here? Okay. So let me briefly talk about the variational inference here. The problem, I think most of you know the principle of maximum likelihood estimation, right? This is the maximum likelihood estimation, but this problem is super hard to solve because this summation involves many terms. And we find a lower bound here. When we maximize this lower bound, we are actually maximize the likelihood. Okay. The maximization of this lower bound involves two things now. Remember here, you only care about the model parameter, right? The embedding vector, because the hidden variable will be marginalized out. But in this lower bound, you care about two things now. One is a variational distribution or its parameters, and parameters of your original model. Okay. So this is the setup of variational inference. So basically, you're still solving an optimization problem, but now you have two parts to solve. One is to optimize the original model parameter here, and also parameters of variational distribution. The good thing, you don't have this log sum anymore. From this lower bound, when you optimize the parameters of your original embedding model, remember this model contains all your embedding vectors, right? This model will be, so for some selectors, their weights will be decided by this posterior distribution, right? So with good selectors, you get higher posterior probability. They will play an more important role in the optimization of the embedding model. And then variational inference. So this problem is hard in the sense that we want this model to work fast because there are many pairs to embed, right? First, exact solution is not tractable. I mean, this is usually the case in variational inference. Even for mean field distribution, we decompose the posterior probability to like the product of marginal probabilities. Still, you cannot calculate or closed form solution here because of the non-conjugacy. At the same time, we have the requirement of computational speed, right? And we use amortized inference. So amortized inference works like this. Instead of optimize the posterior distribution every time for every pair, instead you train a neural network with the input of your data, and this neural network will directly give you like almost the optimal solution for the posterior for your variational distribution here. This is the principle here. But building this neural network is not an easy problem in this situation. Why is that? Because you want your neural network to have all the information related to this optimization problem, right? Meaning that you want the item, you want to predict the context. Remember, this context has varied lengths, right? Sometimes there are 5 items, sometimes there are 3 items. So this is one problem you need to consider. And also embedding vectors. These embedding vectors are associated with the embedding items. So they also have varied lengths. No, there are varied number of these vectors. Okay, so, and also the prior probability of the context item, another vector with varied length. Okay. This is one big issue. So basically, we need all the work below is focused on solving this problem. Direct input. This one is problematic, right? And we have tried a very naive method. We just take a vector with all items, and we use flags to indicate which item is in the context, and then we like allocate that long hidden vector with some entries to fix it to be zeros. But this kind of input is not compact, right? It's super sparse. So the information is decided by the locations of non-zero entries, not their values. This is bad. Okay. In our computation, one observation we have is we can first eliminate the indices of items by do some pre-calculation, right? So in the original embedding model, we have this type of calculation here. So basically, we take for these context items, we take their vectors, and then we take vector inner products first. We get some values. Now we don't care about the indices of context items anymore, right? We only care about the results of these inner products. So now we have a little bit more compact input. So the count of the atom to be predicted, sum scores, or inner product results. Still fully factorized distribution. Still meaning mean field variational distribution. No, the input. the output is always one bit, one float number, the probability. So a sum of what? Yeah. Yeah. No. So the space is still large because of the size of your contact. You can have exactly. Yes. Exactly. That's still mean field variational distribution. Yeah, one by one. But input is strange. Okay, so the input now is the item count to be predicted, and a series of inner product results. Okay, so still here in this is not a vector. This is like a list of numbers with varied length. Again, this is another varied length list. Okay. Still, you cannot directly fit in these numbers into a neural network because most neural network only takes fixed length vectors. Okay. How do we overcome this problem? So here in this page it is mean field distribution. So the output is still is for one bit of the hidden variable. In this input, there is another thing to consider because of this symmetry of contact items, right? You're using a neural network for different bits in this vector. So the network itself don't know which bit it is predicting, right? The input for the neural network is the same if you don't make the difference. So let me repeat. So here you have a set of items. You're going to use your neural network to predict for every item in the set. And the input to the neural network is the same for every item in this set. How does the neural network know which bit it is predicting? Okay. So the trick we are using here is for this item, for values corresponding to this bit I'm predicting, I take out their values. The rest of values will occupy like some bandwidth. And for values corresponding to this bit, they are separate, they are special, they take special input in this neural network. When I move to the next element, I'm going to predict. Okay, and then I make their corresponding inputs special. They take special slots in the input. All others will use the same bandwidth. Okay, this is the principle here. And this is the taking out special entries from the input list. Okay. And then we use some binning technique to handle the varied length list of numbers. So here we have several values, 5, 6, 9, any values. And we use a fixed number of bins, soft bins, and get bin weights from these inputs. And here, the counts at each bins, at different bins, will be a fixed length vector. This will be the input to the neural network. This is the final structure of the neural network. Now after we have done apply the binning technique, we get fixed length vectors from values corresponding to other contact atoms and values from the contact item I'm predicting, and some other, the count of the target item. So, and then I can use my neural network now. Okay. This is our reusable model, and then I get a form of this trainable variational distribution, and then I can optimize this neural network and also the embedding model together to maximize the lower bound, indirectly maximizing the data likelihood or pseudo likelihood. So this is the entire algorithm. Questions here? Go ahead. Yeah. Yeah. Well, I think this is our main principle of when you model your copy of your data, right? When you apply a statistical model, you're certainly losing some information. The thing is what information you care about, and then you specially design your model to capture that part of information. In terms of the part you're talking about, maybe you're thinking, okay, different users, there are some user groups, they have different behaviors. So if you want to characterize such information in your model, you can consider user hierarchical model or like a mixed model, right? One mixture is for one group of users. This user belongs to this group and they share some common behaviors. Another group. So this is the type of thinking for like getting information from the data. Here we care about the general relation among items shared by all users. Other questions? Okay. Anyway, this part of math is dense. But the general idea is you have one target you want to predict. There are a sequence of contact items. Some items are not related. Somehow we use a probabilistic model to infer which item is not related to the target. We like downweight, I would say, these items, downweight effect of these items in the embedding model. So this is the whole idea here. Okay. And then we run some experiments. So we compare the predictive log likelihood, pseudo log likelihood. Our model basically get better pseudo log likelihood in terms of like predicting power, predictive power. We also do some similarity comparison between movie genres and similarity between our embedding vectors. And we found out the embedding vectors found by our context selection model is more consistent with movie genres. Okay. So basically, we take one movie as the query and rank other movies by their distance computed from embedding vectors. At the same time, we take one movie, rank their neighbors by movie genres. So certainly, we used some type of distance. Because each movie is tagged by several genres, right? So here we see that our our the distances from our embedding model is more consistent with movie genres. Okay. And we have one example like one imaginary market basket, one shopping basket here. So this is the entire shopping basket, right? So we take out one item as the target item. We're going to predict this item. With our embedding vectors, basically, these items are less related. So they are less likely to be in this context. Similar, we take out cat food joy and other cat food pet supplies will be more related. So this is in an imaginary bucket. So we believe this type of phenomenon is happening in the real data too. Okay. So here is the conclusion. With our zero inflated distribution and also context selection model, we can purify the target context relations. And then in the embedding model can focus on relations we care about. So with our two models, we found out the embedding quality is better than competing models, baseline models. Okay, I would like to thank my collaborators, David Lai and Francisco Ruiz, and thank you guys.